All right, we are about to embark on the world of transformations, specifically with parent functions. So first off, what we're going to do is we're going to start with a function that we already know. Our friend, the quadratic function. So we have our standard form, f of x is equal to ax squared plus bx plus c. We all know that that is pretty and useless. It doesn't tell us a lot, so we need to make sure that we are in vertex form, which is given here. Now, if I go back to what we did last time and I say, here is my quadratic function, and if I have my general form, I want to know what's going to happen if I substitute in key numbers into the x value and what numbers come out. So we know that I have my vertex at 0, 0 of the original. I know I have key points at 1, 1 and negative 1, 1. And the other ones are at 2, 4 and negative 2, 4. So again, here I'll highlight them on my diagram. So key point 0, 0, 1, 1, negative 1, 1, 2, 4, and negative 2, 4. Those are my 5 key points that I'm going to be working with. My domain for all parabolas is x is an element of real numbers. My range for this generic parabola is y is everything greater than or equal to 0. Y is an element of real numbers. So this should look familiar to all of you. Now, because we're starting with something we already know, we're going to use this and apply it to what we don't. So what I want everybody to do is I want you to log on to Haiku. When you log on to Haiku and you scroll down to the bottom of the functions section, so here is our lovely Introduction to Functions tab. And if I scroll down, you will see a GeoGebra transformation of functions. In the bottom right-hand corner, it says View as Pop-up. That's what we're going to do. So when you view it as a pop-up, this is what you see. Now, you'll notice here that it says f of x is equal to x squared. That's the generic function in red. As I change certain values, my g function or my transformed function will showcase. You'll see here there's a point P, 416. That's a generic anchor point. Notice Q will also change accordingly. So let's try one together. So this one here says x minus 3 squared minus 4. In your head right now, you should be able to tell me that the equation for the axis of symmetry is at x equals 3. You should be able to tell me that the vertex is at 3, negative 4. You should be able to tell me that this opens upward. So here at 3, negative 4 is my vertex. It opens upward. There is no stretch factor, so I know that one point is going to be 1, 1 away like this, and then 2, 4 away like this, and like this. So I should be able to draw my generic parabola that's been transformed according to these transformations. The domain is x is an element of all real numbers, and I know that my range is y is everything greater than or equal to negative 4, and y is an element of real numbers. Now I'm going to use the program to show that this is exactly what's happening. So let's go to our pop-up window here, and it was x minus 3, so that's the, let's see here, if I change this. So notice if I change the k value, it's changing the b, quote-unquote, b value in the stretch, so that's not what I want. The a value is the stretch factor in front, again, not what I want. Here, let's try C. C, what does C do? Oh, there it is. That's moving it up. So good, I want to move down 4. 1, 2, 3, 4, like this. And notice D is here. Well, I want it to say minus 3 in the bracket. You can also type, that will work for you, not a big deal. So notice in red is my original function right here. And notice in blue is my transform function. Notice here my key point, which was originally at 416, has now moved to 712. Just confirm to yourself if this point 416 went 3 units to the right, 1, 2, 3, and 4 units down, 1, 2, 3, 4, I would end up here at 712. So I would like you to tackle these two questions. You may use the software, or you may use your generic understanding of how to transform quadratics. So everybody give that a try, please. Well, here if I look at my example of negative x minus 4 squared plus 2, here are a couple of things I notice. I know my equation of axis of symmetry is at x equals 4. I know my domain is the same. Notice here I have a negative sign, so it got reflected in the x-axis. And because it got reflected in the x-axis, it opens down. Therefore, my range is y is less than or equal to 2, and my vertex is at 4, 2. Again, here are my key points. Because there was no stretch factor, I was able to plot those exactly. Now here I have a stretch factor by a factor of a half. I know that my equation of the axis of symmetry is at negative 4. Because there's no value here at the end, I know that my vertex is at negative 4, 0. Again, notice that it's a little bit wider now because of the stretch factor, and here's my lovely parabola. Okay, last one. We're going to give this one a try, and then I'd like you to try the summary. So please pause the video and give it a go. So this is our last example in the quadratic section. So here I have a reflection in the x-axis. I have a vertical stretch of a factor of 2. I went 3 to the left and 10 up. So my equation of the axis of symmetry is that x equals negative 3. So if I want to draw that on here, I can. I have a vertex at negative 3, 10, which is up here. Because my stretch factor is a factor of 2, instead of going 1 over and 1 down, I'm going 1 over and 2 down on either side. Instead of going 2 over and 4 down, I'm going to go 2 over and 8 down again on either side. Here's my beautiful parabola. I know according to the generic formula, I have a vertex at h and k. Please remember to put it in brackets. The equation of the axis of symmetry is always x equals whatever h is. It has to be x equals. The domain of all parabolas is x is an element of real numbers. The range has to deal with k. So if it opens up when the a value is greater than 0, and it opens down when the a value is less than 0. So the range is dependent on the a value. So you can say y is either greater than or equal to k, or you say y is less than or equal to k, depending on if it opens up or opens down. So this is if it opens up, and this is when it opens down. All right, so not too shabby. I want to take a moment here and pause briefly to take an aside. So if we want to relate this to the point notation that I did with you last class, this is how it would look. So according to the example that we have here, our last example, where f of x is equal to negative 2 x plus 3 squared plus 10. And if I said to you, I have a generic point x, y, and I want to transform that point, remember that this is x minus 3 because it goes 3 to the left, that it's negative 2 times y, and then you add 10 because it went 10 up. So if I change this into point notation, and I pick an example of a point, let's say on my original quadratic function, 0, 0 is a point. This point now goes to 0 minus 3 is negative 3. Negative 2 times 0 is 0 plus 10 is 10. Oh, look, that's my vertex point right here. Let's pick another point, 1, 1, just for the sake of argument, 1, 1. That point now goes to 1 minus 3 is negative 2. And then if I substitute in 1 for y, I get negative 2 plus 10, which is 8. So negative 2, 8 is this point right here. If I continue to do this with the other key points, i.e. negative 1, 1, 2, 4, and negative 2, 4, I will get the corresponding points here, here, and here. So regardless if you choose to do this with what you know about quadratics already and their transformations, we can now also do the same with our point notation. I'm hoping at this point that this connection between the original transformations of quadratic functions, which you did last year and earlier this year, and what we just did with transformations of generic functions, these two connections are now obvious to you.